Alrighty, let's see here. Just getting cleaned up here. Get status. Okay, everything's good. And I'm starting on I'm resuming chapter 20. We didn't get very far yesterday on chapter 20. Just because I just running a little bit. I was a little bit exhausted, and I didn't want to be late to dinner, so kind of wrapped a little early. But yeah, so we're at 22 signals, types, and default actions. And this morning was kind of slow for me, so might need to get some more coffee in me to get through all this stuff. But we got 3 chapters of signal stuff, fundamental concepts, signal handlers, and advanced features. A lot of this, I would say probably about 60% of this is review for me, but there's a good chunk. A lot of it is stuff that I haven't encountered before. So excited to dive in here and yeah, get started on the signal stuff. So let's start on signal types and default actions. So earlier we mentioned that the standard signals are numbered from 1 to 31. Yeah, so there's like I think there's a man signals. Sorry, let me history grep for man, because there's something as signal, not signals. Yep. So that's man 3 signal. I think there's a man 7 signal. Yeah, this one here. So this has this table of all the different signals. I think there's one, yeah, here. See, these are the standard signals, signal number for standard signals. So basically 1 to 31. Sorry. So 32, I guess 60. Is that not a signal? Let's see. Is 0 a standard Unix signal? It is used only for error checking. Kill pid 0 does not send a signal, but instead checks whether the process exists, checks whether the calling process has permission to send signals to it. Interesting. The return value tells you the result 0 process exists and has permission, and then it gives you back an error if it doesn't. It's portable. That's cool. So there is no like signal 0, but 0 is used as like a sentinel value to verify the signals can be sent to a process, that the process exists and you have the permissions to do so. And then sig 1 to 31. I'm just gonna kind of read through these because some of these are reviews. So sig hup is hang up, which I've only really encountered as a way of reloading configuration. Sig int is sig interrupt, which is control C, basically to end, and the execution of the process. Sig quit is similar, as well as sig kill, but these are, I think sig quit is kind of like a soft signal to kill, and then sig kill, I don't think you can prevent sig kill from happening. I think that's the power of sig kill. Sig ill, I don't know what that is. Sig trap is probably when a breakpoint gets hit, a breakpoint instruction, trap instruction. Sig abort, I've definitely ran into this before, but I forget what triggers it off the top. It's not on the top of my head. Sig IoT, definitely not Internet of Things. Don't know what that one is. Sig bus, I've seen this one before, but I don't know what it is off the top of my head. EMT, FPE. USR 1 and 2 are basically like for the application to have custom signaling. It's kind of like an application level signal. SIG-SEG-V is a segmentation violation, so you've reached into a memory address that you're not allowed to. SIG-PIPE, I'm not sure what that is. I think this is like, to be honest, I don't know it. SIG-ALARM, SIG-TERM, terminate. Let's see, SIG-STK-FLT, SIG-CHILD, SIG-CLD, SIG-CONTINUE, SIG-STOP. I think stop and continue are the when you hit Control Z and then FG to resume, or BG. SIG-TS, TP, SIG-T, TIN, TTOU, URG, XCPU, XFSZ, VT alarm, virtual terminal alarm, prof, winch, winch. That's when the winch on your Jeep gets stuck. It says a SIG winch. SIG IO, pole, power, info, lost, sys, and then sys and unused. I read the other day are the same. And then based on your architecture, the numbers might change. But they're pretty conserved overall. Cool. Real-time signals. I think there's like an extended table somewhere. I guess not. Let me ask. In Linux, is there a man page for Linux specific signals? TMIN. So they're documented, but they're not in this table here. This is only for standard signals. Okay. At some point, I would like to read this man page. Maybe we'll do that. There's 2 man pages. There's man 7, and then man, I think I do -A signal. So there's 3P, 2, 7. So maybe we'll start with 2. Which will be the standard library. And then there's also a man 3P signal. So I'll just get them all open there. I kind of want to read these first before we dive into the chapter, just to get a good overview. All right. Or maybe, I don't know. I think I want to read these up front. But yeah, I need to use a restroom real quick, and then I'll dive into the man pages there. So I'll be right back. All right. Oops. Let's just do... What I really want is to take this over to here. Maybe here? Yeah. And... maybe do this. Yeah. Oh, interesting. Oh. There we go. A little bit more room. Okay. All right. Signals. This is a 7-man page, which is miscellaneous information manual. Overview of signals. Linux supports both POSIX reliable signals. So there was a period of time where signals were not reliable. That's mentioned in the book. And then Unix implemented these reliable signals. And so Linux supports the reliable signals, hereinafter known as standard signals, and POSIX real-time signals. Signal disposition. Each signal has a current disposition, which determines how the process behaves when it is delivered the signal. The entries in the action column of the table below specify the default disposition of each signal as follows: term, ignore, core, stop, continue. Term, default action is to terminate the process. Ignore, default action is to ignore the signal. Core, default action is to terminate the process and dump a core. Stop, default action is to stop the process. Continue, default action is to continue the process if it is currently stopped. A process can change the disposition of a signal using sig action or signal 2, which is both of those are syscalls. The latter is less portable when establishing a signal handler. See signal 2 for details. Using these system calls, a process can elect one of the following behaviors to occur on delivery of a signal: perform the default action, ignore the signal, or catch the signal with the signal handler. A programmer-defined function that is automatically invoked when the signal is delivered. By default, a signal handler is invoked on the normal process stack. By default, a signal handler is invoked on the normal process stack. So it's almost as if you've called into it from your function that you're currently processing. It is possible to arrange that the signal handler uses an alternate stack. See sig alt stack for a discussion on how to do this and when it might be useful. The signal disposition is a per process attribute. In a multi-threaded application, the disposition of a particular signal is the same for all threads. So signals are handled on the process level, not on the thread level. A child created via fork inherits a copy of its parent signal's dispositions. During an exec, the dispositions of handled signals are reset to the default. The disposition of ignored signals are left unchanged. So the disposition of handled signals are reset to default because there is no longer a signal handler, or the exact process likely doesn't have the same signal handlers as the process that exec it, because you blow away the text of the program when you exec. So that's why they set these back to default. But then anything that's ignored remains ignored. Sending a signal. The following system calls and library functions allow the caller to send signals. So you raise, send a signal to the calling thread. kill sends a signal to a specified process, to all members of the specified process group, or to all processes on the system. PID FD send signal. So this is a library function. Sends a signal to a process identified by a PID file descriptor. Kill PG sends a signal to all the members of a specified process group. pthread kill sends a signal to a specified POSIX thread in the same process as the caller. pthread kill. Huh? I thought you just said that the signals go to all threads of the process. The signal disposition is per process attribute. In a multi-threaded application, the signal disposition of a particular signal is the same for all threads. Oh. So does that mean that you can send it to a specific thread? It just happens to share the same disposition with all threads? Interesting. pthread kill sends a signal to a specified POSIX thread in the same process. I didn't understand that when I read that initially. That's good to know. TG kill sends a signal to a specified thread within a specific process. Well, there you go. This is the system call used to implement pthread kill. Makes sense. SIGQ sends a real-time signal with accompanying data to a specified process. So real-time signals I don't have such great familiarity with. Oh, this is long. Okay. Alright. Waiting for the signal to be caught. The following system calls suspend execution. So I've seen pause. Tried using that when I started on this book for something. The following system call suspends execution of the calling thread until a signal is caught or an unhandled signal terminates the process. Suspends execution until any signal is caught. Sig suspend temporarily changes the signal mask. See below, and suspends execution until one of the unmasked signals is caught. So you suspend, you unmask one of the signals, and then once it's caught, both of these syscalls require you to catch. So there has to be a signal handler. Synchronously accepting a signal. I'd like to get pause going here. So let's jump over to chapter 20 if I have that. No. MKDR chapter 20. And then we'll just ls here. It's going on 18, chapter 18. Alright, we'll rsync avzci, chapter 18, into chapter 20, cd, oh, what do you mean rsync? Rsync, cd into there, and then rm threaded exercises, and then lt, we'll say L9 ref, yeah, and then we can rm rf ref ders links. Yeah, I'm just gonna blow away all of ref because I don't think I need it right now. And then if you open up makefile, okay, that looks good. So we're gonna open up a pause resume.c. We're gonna give me a little bit more room here to read. Let's do a main, and then in here printf about to pause, and then we'll pound include standard io.h. Here we'll pause, and if I do a quick man2 on pause, we're going to see that it's a void star int, and then this will be int ret is equal to pause, and then we'll print out a here. I need a new line here as well. Oops. Delete in that and say pause return was %d new line, give it ret, write that out. We're gonna need unix standard.h, unistandard.h, there we go. That'll give us that, and then we also need standard lib for the constant there, stdlib. Okay, and then we need a handler here. We need to wire up the handler as well. So we're just say void handler, and it does nothing but we can maybe do a printf. Oops. Handler invoked, and then we need to wire up our handler, which I don't know if we got some C code here. Doesn't look like it. If you go up here, look for handler, execution of signal handler. This is more mechanics. Maybe we just ask an AI real quick here. Just say, give me the C code to register a basic signal handler for SIG USR1. SIG action. Okay. So we have our void. It receives a int sig no. I don't know why it needs to be static. Why does the handler need to be static? Handler does not need static for correctness. Internal linkage. The symbol is not exported outside of this translation unit. Other C files cannot refer to it. It may reduce symbol table pollution and avoid name collisions. Has nothing to do with, okay, great. So it's not needed. So you have our handler. Here we're just gonna why does it say that? Okay. Here I'm gonna leave that off because I don't have the warning. And then I'm gonna pass in the sig no. And this would be %d. Cool. That's all good. And then in the main, what do we have to do here? We have to create a struct. Struct sig action sa, and then sa.sa handler is equal to handler and sig empty set. I don't know what that does. No signals blocked during handler. sa.sa mass. Okay. And then sa.sa flags is equal to 0. If sig action, and then we register it. Okay. Grab this guy. Oops. Come on. So this thing takes in sig USR1. So we're going to need some new headers here. So we're going to pound include our signal.h. That'll probably handle a bunch of them. Signal.h. Great. sig action, sig USR1, SA, no, -1, sig action. Yep. Looks great. So now it's registered. And then this thing says, okay, here's my PID, just print it out. Okay, this is helpful. And then this goes in a loop and pauses forever. So looks good. Cool. So that should work then. If we just do make, and then we can run the build, pause, resume. Kill, I'll just copy the command here. Oh, I definitely copied that right. There we go. So about to pause, and then handler, it was invoked, and then pause returned to -1. That's interesting. If we do man pause on 2, return value pause returns only when a signal was caught, and the signal catching function returned. In this case, pause returns -1. In this case, pause returns -1, and error note is set to E enter. Signal is caught by the signal catching function returned. So why do we care about that as an error? I don't think we do. Okay. Totally works. It runs until it pauses, and then we send the sig USR1. This would be 7807. And then it resumes. Cool. Let's go ahead and run man7 signal again. So, sig suspend. Temporary change in signal mask. See below, suspends execution, synchronously accepting a signal. Rather than asynchronously catching a signal via signal handler, it's possible to synchronously accept a signal, that is, to block execution until the signal is delivered, at which point the kernel returns information about the signal to the caller. There are two general ways to do this: sig wait info, sig timed wait, and sig wait. Suspend execution until one of the signals in the specified set is delivered. Each of these calls returns information about the delivered signal. Signal FD returns a file descriptor that can be used to read information about signals that are delivered to the caller. Each read from this file descriptor blocks until one of the signals in the set specified in the signal FD call is delivered to the caller. The buffer returned by read to contains a structure describing the signal. Interesting. Let's do maybe a man on sig wait. See if they have an example program though. They just have the. Let's do man2 sig wait info. Is there any examples? No. What about sig timed wait? No examples on that. Okay. Hopefully the book covers that. Not sure I fully understand how I would go about using this functionality here. Signal mask and pending signals. I've encountered this before. A signal may be blocked, which means that it will not be delivered until it is later unblocked. Between the time when it is generated and when it is delivered, a signal is said to be pending. Each thread in a process has an independent signal mask, which indicates the set of signals that the thread is currently blocking. A thread can manipulate its signal mask using pthread's signal mask. In a traditional single-threaded application, sig proc mask can be used to manipulate the signal mask. A child created via fork inherits a copy of its parent's signal mask. The signal mask is preserved across exec.ve. A signal may be process directed or thread directed. A process, okay. I'm gonna have to reread this because I don't fully grok this. So a signal may be blocked, which means that it will not be delivered until it's later unblocked. Between the time when it is generated and when it's delivered, it's said to be pending. And so those things, the pending signals, they wait for you to unmask. Each thread in a process has an independent signal mask. I thought before the disposition was shared between all threads. Didn't it just say that back up here? The signal disposition is a per process attribute. In a multi-threaded application, this disposition of a particular signal is the same for all threads. So they're saying disposition is same for all threads. And okay, so a signal has a disposition, but masking of it is different for each thread. Masking is not the disposition. The disposition is like, what do I do when this signal gets hit? Do I terminate? Do I ignore? Do I core dump and terminate? Do I stop the execution? Do I continue execution? I would think part of the disposition would also be, do I invoke a handler? Right? Each signal has a current disposition which determines how the process behaves when it is delivered a signal. The entries in the actions column of the table below specify the default disposition for each signal as follows. Process can change the disposition of the signal using sig action or signal for details. Later is less portable. Okay. Using these calls, a process can elect one of the following behaviors to occur on delivery of signal. Perform the default action, ignore the signal, or catch the signal. Okay, so these 5 things are default actions. You could then say, I don't want to do the default action, I want to ignore it. Or I don't want to do the default action, I want to run my own signal handler. And then on top of that, each thread can mask. So the disposition is independent from masking, is like what I want to just underscore there from what I'm reading here. So each thread in the process has an independent signal mask, which indicates the set of signals that a thread is currently blocking. A thread can manipulate its signal mask using pthread sig mask. In a traditional single-threaded application, sig proc mask can be used to manipulate the signal mask. A child created via fork inherits a copy of its parent's signal mask. The signal mask is preserved across exec.cve or exec.ve. A signal may be process directed or thread directed. A process directed signal is one that is targeted at and thus pending for a process as a whole. A signal may be process directed because it was generated by the kernel for reasons other than a hardware exception, or because it was sent using kill2 or sigq3. A thread-directed signal is one that is targeted at a specific thread. A signal may be thread-directed because it was generated as a consequence of executing a specific machine instruction that triggers a hardware exception, e.g. sig segv for an invalid memory address or sig fpe for a math error, or because it was targeted at a specific thread using interfaces such as tgkill and pthreadkill. So one thing I did want to do is spin up some threads here. So the thread code will be like, okay, we got our handlers set up, we omit that, and then here we want to do our thread code. And if I jump over to the Linux programming interface, there was cat chapter 18 threaded get current working directory. So this has a couple threads. So we'll just say, hey, this is our thread func. I totally copied that correctly. Okay, so we've got a thread func. The only thing that this thing needs to do is this stuff with its ID. So I guess I need to bring back the ID. There we go. There we go. And then grab this stuff here. So we have it about to pause, paused, pause return for thread percent, or how about we just say this, DT colon pausing thread, and then here we give it the thread ID. It's a long, so I gotta do L here. The pause return, I don't really care. Returned DT colon, we'll just say unpaused. Oops. The return here I don't care about. We'll just say unpaused thread percent %LD. This will be thread ID. Oops. What? This format specifies long, but argument type has void star. Well, we could. Oh, it needs to be ID, not thread ID. ID. There we go. Non-void function. Can I just do like a void function here and just say void like that? I think I can do that. Okay, then we need to create our threads and join. Pthread create is going to require pthread.h. And then incompatible, maybe start routine can be a reference to that. No, okay. So it has to be a void star. It's a little bit odd. And then here, return null. There we go. Okay. So maybe we wait on this printf until after we've created our threads. Then we join here so that we're not potentially dealing with, I guess it could, yeah. I guess the threads should be running. So here we can pause as well, right? Oh, did I lose my pause here? I didn't notice that. Okay. So here, I'm gonna say pausing main thread, unpausing main thread, and then we'll just DT slash bam, oops, and then DT paren bam. Oop. All right, so I can close that out, write that, make build pause resume. See, so we can see here we pause thread 2, the main thread, and thread 1, and then we're gonna do our asynchronous thing. Handler was invoked, and then we unpaused main thread, and then we got blocked on the other 2 threads. So let's do that again. I want to see just a sampling of like main thread again. Main thread again. So if I vim up the pause resume and I delete this pause here, so we're just waiting on the threads, will it unpause one of them? Let's go ahead and make, go ahead and run it. And then let's go ahead and do our kill. Oh. Handler was invoked, but we returned to executing the join. We didn't actually unpause the thread. Okay, let's see if we can target specific thread. So the first thing we'll need to do, let's do pause resume here. So I'll bring back the main pause, kill this for a second. What we need to do is get the thread IDs, the task IDs, I think it's called. So if we do like man get task ID, get TID, here we go. Get thread identification. Okay, so that's in the Unix standard. So this thread ID is not helpful, so I'm gonna just say don't pass it in. So thread is here, null, thread punk, new thread, T1. And then the argument, I'll leave it, but I'll say, actually, you know what? I'll just go ahead and delete all that. And then the arg, we'll just say null, because I don't really need that. It's not really helping anything. Okay, so now we got our threads running, but now we have to say here, what is this? TID, which is a PID T, is equal to get TID void, bam. And then this will be a TID here and TID here. And it says, hey, get TID does not work, so we need to do our pound defined. I think I can say default source, and that'll work, right? If I spelled that right, default source. No? Okay. We'll say GNU source. Why is it not working? Get TID PID include uni standard. Just go and copy this. Might just be the static analysis is a little bit off. Why is that syscall not available there? Well, let's see if it builds. Does not. Get TID. Let's ask AI here. Say, hey, how do I get the thread ID from a call, a syscall, inside the thread? Get TID, TID. Maybe I need the systypes thing. Doesn't seem like something I would need. Get TID, TID. Maybe I'll just do this then. Syscall, and then give it the sys get TID. Why would that not be available? This is so annoying. Let's go ahead and copy this. Well, that's Gemini. Say on Linux. Yeah. I mean, at least it says the pound define good news source, right? Maybe I need to put that up at the top. So we'll leave that. Put the good news source up at the top. There we go. Now everyone's happy. You need to have the good news source at the top. Alright. Let's go ahead and make. Alright, still doesn't like it. It says, hey, I expected a void star, void star. Okay, we can say a void star X. You know, we don't need that. Okay. Build, pause, resume. Okay. Ooh, my foot itches. Alright, let's go back here. Okay, pausing thread TID. We'll just run it like this. Main, like that. And then here, that's weird because get PID, is that long? There's a PID T. That is a PID T. Okay. So let's go back to LD here then. Or long of the TID. And if I do man on kill, kill USR1 PID or name. Here, let me ask Gemini, is it possible to use the kill command line to send a signal to a thread ID? Kill a single thread and leave the rest of the process running using signals. For that, you would need to use pthread cancel within your code. Yeah, okay. Alright, so seems like kill just works out of the box with the thread ID. So I'm not going to say main, I'm going to say thread here. Oops. There we go. Alright. Let's go ahead and make that. And then we're going to need two terminals. We're going to run build, pause, resume. And then I'll go ahead and kill a thread here. So let's try killing this one. Okay, handler invoked, unpause thread. And then I can kill this one. Oh no, sorry. This one. So now both threads are unblocked, so I can now kill the main thread, and it should resume. Yep. And I can do those in any order. Like I can say, hey, let's do the main first. And then here. And it's still blocked on the last one. Damn. Sorry, I didn't copy it right. Yep. Cool. Works as expected. Let's go back to Gemini. I want to resume my conversation with it about I guess it's not in the history there. So on Linux, a thread ID would never, how do I say this? A given thread ID from get TID would never be used for a process ID from get PID or get PPID. These sets, the set of thread IDs is non-overlapping with the set of PIDs, process IDs. Yeah, it shares the same number space, but they're not overlapping. Come on. Can you understand what I'm saying here? Because of how Linux kernel handles execution of a process, it really just a threaded group. It leads a few specific rules about how these IDs overlap. The main thread rule: when you start a new process, the kernel assigns it a PID. In Linux, the main thread of the process is automatically assigned a TID that is identical to the PID. Example. Okay, so they are overlapping because the PID is the same as the TID for the main thread. I guess that's right. Okay. The global uniqueness rule: TIDs are globally unique across the entire system. Since the main thread's TID is the PID, the kernel ensures that no other process or thread can take that number. If you spawn a second thread, thread B, within the same process, the kernel will look for the next available ID in the global pool. Okay. So PIDs and TIDs are the same number space. Cool. Well, that was fun. Let's go back to man 7. I'm going to go down further. So we covered the synchronous stuff, masking. Here it is. Each thread is in a process as an independent signal mask, which indicates a set of signals that can be the thread is currently blocking. A thread can manipulate its signal mask using pthread sigmask. In traditional single-threaded applications, sigproc mask can be used to manipulate signal mask. A child created via the fork inherits a copy of its parent signal mask. The signal mask is preserved across exec VE. A signal may be process directed or thread directed. A process-directed signal is one that is targeted at and thus pending for a process as a whole. So what I've observed in my testing here is that if you send a signal to a process, it goes to the main thread, which means that if it has a signal handler, the signal handler executes on the main thread, suspends the main thread, executes on the main thread, and resumes on the main thread. A signal may be process directed because it was generated by the kernel for a reason other than hardware exception. I think we already read all this. A process directed signal may be delivered to any one of the threads that does not currently have a signal block. Okay, so process directed signal is different than using kill on a PID. I think that's still a thread directed signal just to the main thread, because the main thread has the main the task ID or thread ID. I think this is a different concept. So signal may be process directed or thread directed. A process directed signal is one that is targeted at and thus pending for a process as a whole. A signal may be process directed because it was generated by the kernel for reasons other than a hardware exception, or because it was sent using kill or sigqueue. Okay. A thread-directed signal is one that's targeted at a specific thread. A signal may be thread-directed because it was generated as a consequence of executing a specific machine language instruction that triggered a hardware exception, or because it was targeted at a specific thread using interfaces such as thread kill or pthread kill. A process-directed signal may be delivered to any one of the threads that does not currently have a signal block. If more than one of the threads has signal unblocked, then the kernel choose. So one thing I want to do here as an experiment is let's say here to do mask USR1 for main thread and send the signal to the main thread and see if one of the other threads handles it. I think that'd be a cool experiment to do. So yeah, a process-directed signal may be delivered to any one of the threads that does not currently have a signal blocked. If more than one of the threads has the signal unblocked, then the kernel chooses an arbitrary thread to which to deliver the signal. A thread can obtain the set of signals that it currently has pending using sig pending. This set will consist of a union of the set of pending process directed signals and the set of signals pending for the calling thread. A child created via fork initially has an empty pending signal set. The pending signal set is preserved across execve. Standard signals. Okay. Execution of signal handlers. Whenever there is a transition from a kernel mode to user mode execution, e.g. on a return from system call or scheduling of a thread onto CPU, the kernel checks whether there is pending unblocked signals for which the process has established a signal handler. If there is such a pending signal, the following steps occur. The kernel performs the necessary preparatory steps for execution of the signal handler. The signal is removed from the set of pending signals. The signal handler was installed by a call to sig action that specified the SA on stack flag, and the thread has defined an alternative signal stack. Then that stack is installed. If the signal handler was installed by a call to sig action that specified a signal action on stack flag, and a thread has defined an alternative signal stack using signal T stack, then that stack is installed. Okay. Various pieces of signal related context are saved into a special frame that is created on the stack. Saved information includes the program counter register, i.e. the address of the next instruction in the main program that should be executed when the signal handler returns. Architecture specific register state required for resuming interrupted program. The thread's current signal mask. The thread's alternate signal stack setting. If the signal handler was installed using the sig action SA's sig info flag, then the above information is accessible via the uContext object that is pointed to by the third argument of the signal handler. This object reflects the state at which the signal is delivered rather than in the handler. For example, the mask of the block signal stored in this object will contain the mask of new signals blocked through sig action. Any signal specified in ACT as a mask when registering the handler with sig action are added to the thread signal mask. The signal being delivered is also added to the signal mask unless SA no defer was specified when registering the handler. These signals are thus blocked while the handler executes. The kernel constructs a frame for the signal handler on the stack. The kernel then sets the program counter for the thread to point to the first instruction of the signal handler function and configures the return address for that function to point to the piece of user space code known as the signal trampoline. Yay, this is the first time I encountered the trampoline in my reading. The kernel passes control back to user space, where execution commences at the start of the signal handler function. When the signal handler returns, control passes to the signal trampoline code. The signal trampoline call is sigReturn, a system call that uses the information in the stack frame created in step 1 to restore the thread to its state before the signal handler was called. The thread signal mask and alternate signal stack settings are restored as part of the procedure. Upon completion of the call to sigReturn, the kernel transfers control back to user space, and the thread recommences execution at the point where it was interrupted by the signal handler. Note that if the signal handler does not return, e.g. control is transferred out of the handler using sig long jump, or the handler executes a new program with execve, then the final step is not performed. In particular, in such scenarios, it is the programmer's responsibility to restore the state of the signal mask using sig proc mask. If it is desired to unblock the signals that were blocked on entry into the signal handler, note that sig long jump may or may not restore the signal mask depending on the save sig's value that was specified in the corresponding call to sig set jump. From the kernel's point of view, execution of signal handler code is exactly the same as execution of any other user space code. It is to say the kernel does not record any special state information indicating that the thread is currently executing inside a signal handler. All necessary state information is maintained in user space registers and on the user space stack. The depth to which nested signal handlers may be invoked is thus limited only by the user space stack and sensible software design. So your signal handlers could get interrupted by other signal handlers. Linux supports the standard signals listed below. The second column of the table indicates which standard, if any, specified the signal. P1999 indicates the signal is described in original POSIX 1990 standard. 2001 indicates the signal was added to definition change in SUSV2, and 2001. 2024 indicates the signal was added or its definition changed in POSIX 2024. Oh shit, there's a POSIX 2024. I bet you this thing that isn't updated with that. Let's ask AI. What new functionality or features were added in POSIX 1-2024? Here's a clear, let's pull this guy over here. Pull it up here. Oh. Here's a clear summary of major new functionality and features added in POSIX 2024 standard. Non-standard or only provided as extensions in various systems. So string and memory helpers, format strings with automatic allocation, mem, finding a memory substring, safer strings, the string processing, process environment, fork, lower level fork of variant exit. Okay. Secure getenv, safer getenv for set UID programs. Oh, excuse me. I always like it when API designers add like secure functions. It's like, well, okay, maybe the secure function should be the default one. But I guess that doesn't apply when you have all this legacy they need to maintain for compatibility. File system memory, map anonymous, also known as map anon, standardized for mmap. Realloc array, safer array reallocation. Sockets and file descriptors, except for and dupe 3 standardized. Wow, we're getting really high up there on the versions. New advisory lock operations. Get lock, set LKW, lock right. Conversions and signals, sig2 stir, sig2 sig. Convert between signal names and numbers. Sig winch is now standardized. I'm curious, what is sig winch? What is sig winch? Shell and utility enhancements. Shell changes. Set-o pipe fail is now part of POSIX SH. That's great. Utility add-ons and options, new utility standards, relink, real path, timeout, get text, x get text, message format, etc. Newer expanded options for many commands. Oh, you can rm-d to remove empty directories. Interesting. Instead of doing rmdir, mkdir foo, and I can say rm-d foo, and that works. Never knew that. Sed-e and other enhancements. ulimit, reporting both soft and hard limits. Improved system interface behavior, file seeking. Oh, you can seek to a hole and seek to data. That's nice. I didn't know about those. That really helps with sparse file navigation. You can just seek to the hole. Unicode locale character conversions. POSIX clarifies behavior of multi-byte conversion functions. Revise requirements for so-and-so when buffered. Okay, I don't care about the time handling. 64-bit time T, addressing your 2038 issue in a portable way. Well, that's good that they got that done before 2038. Integration of existing practices. The new standard incorporates APIs and behaviors broadly used in real implementations. GNU, BSD, etc. Many functions previously considered extensions are now POSIX features. The shell and utilities reflect de facto standards found in common Unix Linux environments. Removals, deprecations. Some seldom used or legacy APIs are removed or deprecated based on usage trends. Yeah, okay, I don't really care about any of that. Cool. I want to know what SIG-winch is for. Window size change. Oh, okay. Window change. I thought it'd be like a winch, like a winch on a vehicle. Sig, like winch, like that. One of these things. I gotta text my buddy that. Alright, I'm gonna need to order my lunch here in a few minutes. Alright, so we covered all that. We're going over standards. Abort, timer. So alarm is timer signal from alarm. If we do, I'm gonna clear that. Man on to alarm. Okay. Bus error, bad memory access. Oh. Alright, I'm going to leave off here reading the man page. We'll come back to this later. But I'm going to switch back to reading the book, because a lot of this stuff that is in that section is covered in the book, and I don't want to have to cover it twice. So earlier we mentioned that the standard signals are numbered from 1 to 31. On Linux, however, the Linux 7 manual page lists more than 31 signal names. The excess names can be accounted for in a variety of ways. Some of the names are simply synonyms for other names and are defined for source compatibility with other Unix implementations. Other names are defined but unused. The following list describes the various signals. Say abort. A process set this signal when it calls the abort function. By default, the signal terminates the process with a core dump. This achieves the intended purpose of the abort call to produce a core dump for debugging. Alarm. The kernel generates this signal upon the expiration of a real-time timer set by a call to alarm or set timer. A real-time timer is one that counts according to wall clock time, i.e. the human notion of elapsed time. For further details, see section 23.1. Sig bus. The signal bus error is generated to indicate certain kinds of memory access errors. One such error can occur when using memory mappings created with the mmap. If we attempt to access an address that lies beyond the end of the underlying memory map file, as described in section 49.4.3. Sig child. This signal is sent by the kernel to a parent process when one of its children terminates, either by calling exit or as a result of being killed by a signal. It may also be sent to a process when one of its children is stopped or resumed by a signal. We consider sig child in detail in section 26.3. Boop. Oops. Over here. This one is a libc function, and this one is the what do you call it? Syscall. So I'm not gonna read those pages. Sig child is a synonym for sig child. Sig continue. When sent to a stop process, this signal causes the process to resume. When received by a process that is not currently stopped, this signal is ignored by default. A process may catch this signal so that it carries out some action when it resumes. This signal is covered in more detail in section 22.2 and 34.7. What's the default action for SIG USR1? This one here is to terminate. Interesting. And then SIG HUP. What's the default action for SIG HUP? I don't see SIG hub here. Here it is. Terminate as well. SIG EMT in Unix systems generally, this signal is used to indicate an implementation-dependent hardware error. On Linux, the signal is used only in the SunSpark implementation. The suffix EMT derives from emulator trap, an assembler pneumatic on the digital PDP-11. SIG FPE. The signal is generated for certain types of arithmetic errors, such as divide by zero. Floating point error, is that what it is? Suffix FPE, is abbreviation for floating point exception. Although the signal can be generated for integer arithmetic errors, the precise details of when the signal is generated depend on the hardware architecture and the settings of CPU control registers. For example, on x86-32, integer divide by zero always yields a SIG FPE, but handling of floating point divide by zero depends on whether the FE divide by zero exception has been enabled. If this exception is enabled using FE enable except, then a floating point divided by zero generates SIG FPE. Otherwise, it yields the IEEE standard result of the operands, a floating point representation of infinity. See the FM manual page and FMH for further information. SIG HUP. When a terminal disconnect hang-up occurs, the signal is sent to controlling process of the terminal. I didn't know that. We describe the concept of a controlling process and the various circumstances in which SIG HUP is sent in section 34.6. A second use of SIG HUP is with daemons, e.g. init, HTTP, and inetd. Many daemons are designed to respond to receive a SIG HUP by reinitializing themselves and rereading their config files. The system administrator triggers these actions by manually sending SIG HUP to the daemon, either by using an explicit kill command or by executing a program or script that does the same. SIG IL. This signal is sent to the process if it tries to execute an illegal, i.e. incorrectly formed machine language instruction. SIG info. On Linux, the signal name is synonym for SIG PWR. On BSD systems, the SIG info signal generated by typing Control T is used to obtain status information about the foreground process group. What is this? Control T. Not what I expected, but sure. SIGINT. When the user types the terminal interrupt character, usually Control C, the terminal driver sends the signal to the foreground process group. The default action is for the signal to terminate the process. SIG-IO. Using the FCNTL system call, it is possible to arrange for the signal to be generated when an IO event, e.g. input blocking becoming available, occurs on certain types of open file descriptors, such as those for terminals and sockets. This feature is described further in section 63.3. SIG IoT on Linux is synonymous for SIG abort. On some other Unix implementations, is signals indicates an implementation defined hardware fault. SIG kill. This is the sure kill signal. It can't be blocked, ignored, or caught by handler, and thus always terminates a process. SIG lost. The signal name exists on Linux but is unused. On some older Unix implementations, the NFS client sends this signal to local process holding locks. If the NFS client fails to regain locks held by those processes following the recovery of a remote NFS server that crashed, This feature is not standardized in NFS specifications, so that's completely useless to me. SIG pipe. This signal is generated when a process tries to write to a pipe, a FIFO, or a socket, for which there are no corresponding reader processes. This normally occurs because the reading process has closed its file descriptor for the IPC channel. See section 44.2 for further details. SIG pole. This signal, which is delivered from System V, is a synonym for SIG IO on Linux. SIG prof. The kernel generates this signal upon the expiration of a profiling timer set by a call to set timer. A profiling timer is one that counts the CPU time used by the process. Unlike a virtual timer, see SIG VT alarm below, a profiling timer counts CPU time used in both user mode and kernel mode. SIG power. This is the power failure signal. On systems that have an uninterruptible power supply, it is possible to set up a daemon process that monitors the backup battery level in the event of a power failure. If the battery power is about to run out after an extended power outage, then the monitoring process sends SIG power to the init process, which interprets the signal as a request to shut down the system in a quick and orderly fashion. SIG quit. When the user types quit character, the quit character usually control backslash on the keyboard. Is that a thing? Control backslash? No. This signal is set to the foreground process group. By default, the signal terminates the process and causes it to produce a core dump. So if I jumped over to my chapter 20 and ran my build, pause, resume, and then sent that signal. Okay, I did. Where's the core dump? I don't see a core dump. Maybe it's under build. If I say on Linux, if I core dump a process with SIG quit, where does it go? Cat proxys kernel core pattern. User lib systemd systemd core dump. That's a process. So it goes under var lib systemd core dump. This would just be core dump. Sorry, var lib, not user lib. Var lib system core dump. Yeah, that's where they all are. Lots of core dumps from user ran processes. These are all copy things. Cool, it's good to know. These are all I did yesterday. Or not yesterday, it was on the 13th, sorry. Cool. Alright. Continuing on. Clear that. Using SIG quit in this manner, by default the signal terminates the process and causes it to produce a core dump, which can then be used for debugging. Using SIG quit in this manner is useful for a program that is stuck in an infinite loop or otherwise not responding, by typing control backslash and then loading the resulting core dump with the GDB debugger and using the backtrace command to obtain a stack trace. We can find out. Do you have GDB on here? GDB. Pacman search. varlib systemd core dump core pause. That's annoying that tab completion doesn't work in this directory. Stack, backtrace, no stack. We'll do it here. How do I load a core dump for a executable into GDB? Okay. So it needs the executable first, which would be under build, and then pause resume. Yes. Okay. The core dump is in ZST format. Wow, you're going slow, bro. Oh, you can use core dump CTL. Interesting. Core dump CTL. That's pretty cool. I think I search here for like pause. Yep. Pretty good. So it records the binary path. Doesn't have the dump in there. List. So GDB list, pause. This guy. Hey, look at that. We're in main. It's pretty cool. Not really great with GDB. Okay. Close that out. Don't need that. Let's go back here. Alright, sig-seg-v. Good old sig-seg-v. This very popular signal is generated when a program makes an invalid memory reference. A memory reference may be invalid because the reference page doesn't exist. E.g., it lies in an unmapped area somewhere between the heap and the stack. Process tried to update a location in read-only memory, e.g. the program text segment, or region of mapped memory marked read-only, or the process tried to access part of the kernel memory while running in user mode. And C, these events often result from dereferencing a pointer containing a bad address, e.g. an uninitialized pointer, or passing an invalid argument to in a function call. The name of this signal derives from the term segmentation violation. SIG STKFLT, documented in signal 7 as stack full fault on coprocessor. This signal is defined but is unused on Linux. SIG stop, this is the sure stop signal. It can't be blocked, ignored, or caught by a handler, thus always stops the process. SIG sys, this signal is generated if a process makes a bad system call. This means that the process executed an instruction that was interpreted as a system call trap, but the associated system call number was not valid. SIG term, this is a standard signal used for terminating a process and is the default signal sent by the kill and kill all commands. The users sometimes explicitly send the SIG kill signal to a process using kill-kill or kill-9. However, this is generally a mistake. Well-designed application will have a handler for SIG term that causes the application to exit gracefully, cleaning up temporary files and releasing other resources beforehand. Killing a process with SIG kill bypasses the SIG term handler. Thus, we should always first attempt to terminate a process with SIG term and reserve SIG kill as a last resort for killing runaway processes that don't respond to SIG term. SIG trap. This signal is used to implement debugger breakpoints and system call tracing as performed by strace, ptrace. See the ptrace manual for further information. Cool. I think I'm going to go order my lunch right now because I'm going to want to get off here in a little bit and eat. So I'm going to take a quick break here to order my lunch. Be right back. All right, lunch is ordered. I'll probably eat lunch on stream here this time today, just so I can get reading done without taking a break. Because I want to make more progress on this stuff. So, where we left off here? Sig trap is of course for breakpoints. Sig TSTP. This is a job control stop signal sent to stop the foreground process group when the user types the suspend character, usually Control Z on the keyboard. Chapter 34 describes process groups, jobs, and job control in detail, as well as details of when and how a program may need to handle the signal. The name of the signal derives from terminal stop. Sig terminal 10. When running under job control shell, the terminal driver sends a signal to a background process group. When it attempts to read from the terminal, this signal stops the process by default. Sig terminal TOU, this signal serves an analog to the TIN signal, but for terminal output by background jobs. Instead of input, it's output. When running under a job control shell, if the terminal output stop option has been enabled for the terminal, perhaps via the command stty-to stop, the terminal driver sends sig ttou to a background process group when it attempts to write to the terminal. This signal stops a process by default. Sig unused. As the name implies, the signal is unused on Linux 2.4 and later. The signal name is synonymous for sig sys on many architectures. In other words, the signal number is no longer unused on those architectures, although the signal name remains for backwards compatibility. Sig URG. This signal is sent to a process to indicate the presence of out of band, also known as urgent, data on a socket. Sig USR1 and USR2. The signal and USR2 are available for programmer-defined purposes. The kernel never generates these signals for a process. Processes may use these signals to notify one another of events or to synchronize with each other. In early Unix implementations, these were the only two signals that could be freely used in applications. In fact, processes can send one another any signal, but this has the potential for confusion if the kernel also generates one of the signals for the process. Modern Unix implementations provide a large set of real-time signals that are also available for programmer-defined purposes. I'm curious about real-time signals. We haven't gotten to that yet. Okay, next. Onward. Sig VTALRM. The kernel generates a signal upon expiration of a virtual timer set by calling set I timer. A virtual timer is one that counts the user mode CPU time used by a process. Sig winch, which we discussed earlier, in a windowing environment. This signal is sent to the foreground process group when the terminal window size changes. As a consequence of either the user manually resizing it or of a program resizing it via a call to ioctl, as described in section 62.9. Well, it's at the end of the book. By installing a handler for the signal, programs such as VI and less can know to redraw their output after a change in window size. So like when I'm in a man page here, just say like man to like ioctl. It's like meant for this terminal size, and if I resize the terminal, man could listen on that signal for that signal and redraw its output, but it doesn't. I wanted to try something out here. Where am I at? Oops. Not there. Thank you. So sig x CPU, this signal is sent to a process when it exceeds its CPU time resource limit, R limit CPU described in section 36.3. Sig xfsz, this signal is sent to a process if it attempts, using write or truncate, to increase the size of a file beyond the process file size resource limit. R limit f size described in section 36.3. Table 20.1 summarizes a range of information about signals on Linux. Note the following points about this table. The signal number column shows the number assigned to the signal on various hardware architectures, except where otherwise indicated. Signals have the same number on all architectures. Architectural differences in signal numbers are indicated in parentheses and occur in the Sun SPARC and SPARC 64, HP Compact Digital Alpha, MIPS, and HP PA RISC architectures. In this column, undefined indicates that a symbol is undefined on the indicated architectures. The susv3 column indicates whether the signal is standardized in susv3. The default column indicates the default action of the signal. Term means that the signal terminates the process. Core means that the process produces a core dump file and terminates. Ignore means that the signal is ignored. Stop means that the signal stops the process. And continue means that the signal resumes the stop process. Certain of the signals listed previously are not shown in table 20.1. Sig child, sig info, sig IoT, basically the ones that have synonyms. Okay. I'm so hungry right now. All right. Where are we at now? We are in this table here. I don't really feel like reviewing the data in this table. Notifying ports regarding the default behavior shown for certain signals and tables. I don't really care about these things. It's if you want to read the table, I don't care about the table. Changing signal disposition. Alright, so we got changing signal disposition, introduction to signal handlers. That has a really nice diagram. Excited for that. Sending signals, checking for the existence of a process. So you can send the signal 0. We talked about that earlier. Other ways of sending signals with raise and kill PG. Displaying signal descriptions, signal sets. Some example code, the signal mask, pending signals. Signals are not queued. Changing signal dispositions. Waiting for a signal. And summary exercises. Cool. All right. It is 2:15 abouts. So I'm going to take a lunch break here, and I'll be back in maybe about an hour. Cool. All right, I'll be back in a bit.